Hello everyone. In this lesson, we will talk about the integral of a function raised to the power of -1. As you recall, in previous video, we were talking about indefinite integral of a function raised to a power, and this general formulas applies. So you have u as a function raised to exponent n multiplied by the differential factor of u. So what you need to do, you add 1 to the exponent and you divide it by the result of n plus 1. And don't forget the plus c because we are dealing with indefinite integral in this case. But this formula comes with a condition where n cannot be equal to -1. Because if you take -1 plus 1, it becomes 0. And you cannot divide it by 0 in this case. However, in math, we do have function raised to the exponent of -1, like the hyperbola, right? 1 over x is the hyperbola. So in this case, what we have is we can also integrate that function as well. So if in the case that n is equal to -1 as the exponent for your function, then you have to apply the special formulas. So integral of du divided by u will be equal to the natural logarithm of u, and u is actually as the absolute values, and plus the constant c because we still work with indefinite integral. So let me rewrite these formulas for everyone to clarify that you actually raise this to the exponent of -1. So because I have du divided by u, so I can bring u up as the numerator and I can convert that to the exponent of -1 times du. Okay, so you see now that you have u raised to the exponent of -1 and multiplied by the differential factor of u. So in this case, it will be equal to ln of u and plus c. So let's do a few examples. So we have the integral of x squared times dx divided by 9 minus x to the exponent 3. So in this case, again, you have a function raised to a power. So this function raised to the power of -1. So I can write my integral like this. So the integral of 9 subtract x to the exponent 3, all of it raised to the exponent -1 times x squared dx. So as you remember in previous video, I was showing everyone how to work with the substitution method to let u equal to the function inside the bracket here. Immediately after that, you will take differentiation of this function and then you manipulate your equation to separate your variable and do the substitution for this part. For both part, x squared times dx, and also u raised to the exponent of -1 in this case. So in the end, we are targeting these formulas. All right? Okay. So let's u equal to 9 minus x to the exponent 3. Immediately after, I will find du over dx. So derivative of 9 is equal to 0. Derivative of negative x to the exponent 3 will be negative 3x squared. Okay, so I would like everyone to take a look at this. Okay, so what you do is now you can write this one as integral of u to the exponent -1. And what you have to do is you want to write this part of your integrand in terms of du. Okay, so the one way to do that is to take a look at this equation and manipulate your variable. So what I will do is I will divide -3 over to this side of the equation, and then on the other side I will multiply by dx. Okay, so now you see you have the exact match of what you need to replace for the x squared dx. So instead of writing x squared times dx, so this equation now equal to du divided by -3. So I will write times du divided by -3. Okay, so this one is done. We already achieved our purpose having that, and the other side equal to du minus 3. So what you can do now is you are going to bring this across your integral sign. So that will be negative 1/3 times the integral of u minus 1 times du. So now you see you are having the exact match for this. Okay, you have the exact match for this, right? So you can go ahead and apply this formula. This entire integral will become natural logarithm of u plus c times negative 1/3. So this will be negative 1/3 natural logarithm of u plus c, and all I can do now is just replace the u by 9 minus x cubed, as I have let u equal to. Alright, okay. So 9 minus x to the exponent 3 and plus c as my final answer. And make sure this stay in the absolute values. Alright, okay. So let's continue with the next example. So this example right here, okay, I would like you to pause a little bit and analyze. Take a look at the above one. Okay, so this one, you see, you have x squared times divided by a binomial. So what you do in this case is you bring this entire denominator raised up to exponent minus 1, and then you apply this formula's u to the exponent minus 1. And what you have here, you actually have x to the exponent minus 1. Okay, and you have 3 minus x squared. So what do we let u is equal to in this case? Perhaps we cannot let u equal to. But because I would like you to notice 3 minus x squared, this entire binomial is raised to the exponent minus 1. So if it's raised to the exponent minus 1, you may want to apply basic algebra to manipulate your integrand to see what you can, what formula that you can use. Alright, okay. So what I will do in this case is, because I divided by x, I will apply the concept of fractions. So if I take 3 minus x squared divided by x, I can write it as this, right? So 3 divided by x, subtract x squared divided by x, all of it in the bracket dx. Okay, so you see this is the common denominators here. So you can write this as 3 minus x squared, the whole thing divided by x. So what I did is I break it into two fractions so that I can simplify my my integrand further, and perhaps with the simplified version of this integrand, I'll be able to apply some formula that I have learned already. Okay, so then I will have integral of 3 over x, subtract x squared divided by x. You see, just simply x. So it turned into just x. So square divided by x squared divided by x is x, or you take 2 minus 1 here, it turned into x. So this is dx. Okay, so now I would like everyone to go back and review what we have learned with integration. Okay, so this is a formula sheet that we went over the last time. Okay, so take a look at these formulas right here. This one. Okay, this one. Okay, so you have a sum of difference of the differentiable functions. What you can do is you can break them into individual integrals and then you integrate. So in this case, that's exactly what I will do. Okay, so in this case, what I will do is I will break these integrals into two individual integrals. Okay, so I will write it as the integral of 3 over x dx, subtract the integral of x dx. Oh, okay, so I apply that properties and I break this integrand into two individual integrals. And now you see 3 divided by x. This one is a constant multiplied by, so you can bring that across the integral sign. So I will have integral of 3 times this integral of 1 over x dx, and I subtract the integral of x dx. So this one you can apply the ln. Okay, so you can apply the natural logarithm in this case because you have x raised to exponent minus 1. And this one is actually very simple. Apply the basic rule for the integral. That means you add 1 to the exponent and you divide it by the result of that. So this one becomes your ln of u. So ln of x in this case, right? So let's see. So I just want to make a note for everyone. Okay. Then actually I should say I should write this as x to the exponent minus 1 just to remind everyone. Okay. So that's equivalent to that. Therefore I can write it as 3 times natural logarithm of x as the absolute value, and here this is exponent 1. So I take 1, I add to this exponent, it becomes 2, and divide it by 2. So the integral of x is actually equal to x squared over 2. And the whole thing plus c, because we work with the indefinite integrals. Okay, so you see now you are having this type of integrand, and you don't have to let u equal to anything because your denominator is just a single variable x right here. So you can use your knowledge in algebra to break this into 2, and then we apply all the rules that we know from there. Okay, but for example number 1, what you have in this case is you cannot break this into two integrals because you have a binomial as the denominator. So the only way we can do is we have to let this entire denominator equals to u, and we raise that to exponent minus 1. We differentiate, manipulate to separate your variable, do a substitution method, and there's your result for this integral. So I really want everyone to know the difference between this integrand and also this integrand. Alright, this lesson is actually short, and I have a few, there's only 2 questions for everyone to practice, so make sure that you go over this question and check the solution online. Alright, thank you.